This is Math466, Advanced Applied Analysis, Lecture 29. So we're going to start off today by looking at a chi-squared random variable, and this will lead in naturally to our discussion of the joint density function of eigenvalues of a Gaussian orthogonal ensemble. So we say x has a chi-squared distribution with new degrees of freedom if its density is 1 over 2 to the nu halves, gamma nu halves, x to the nu halves minus 1, e to the negative x halves. Has everyone here seen the gamma function? Everybody's good with that. Okay, excellent. So
wait, all of those things are
news, yes.
The first one's not an R.
The first one is not an R, correct. I would sound more like an R than a nu. So the first question you can ask is, well, what if I have two chi-squared random variables and add them? What kind of distribution do I get? So let's say xk is a chi-squared distribution with nu k degrees of freedom. Okay? So we want to figure out what is the probability distribution of x1 plus x2. And we'll assume they're independent. So the way this works is let's let x be x1 plus x2. Then the cumulative distribution function for their sum is just the probability that x1 plus x2 is at most x. And then once we have the cumulative distribution function, we get the density by just differentiating. So this is just the integral from negative infinity to x of the density function of x at t dt. So then the density function is just, by the fundamental theorem of calculus, just take the derivative. All right, so how would we actually evaluate this? Well, for our case, we have x1 goes from negative infinity to infinity. Well, we've got to be careful. Here, x is in 0 infinity. So x is not allowed to be negative. I'll write it explicitly like this. x1 goes from minus infinity to infinity, and then x2 goes from negative infinity to x minus x1. And then I have the density, I'll call it f nu 1 of x1, and then the density f nu 2 of x2 dx2 dx1. So this is the density. I'd like to do this integral and figure out what is the density. Does it have a nice closed form expression? And the idea we're going to use behind calculating this density is going to be crucial when we do the analysis in a few moments of the joint eigenvalue distribution. I am making an assumption right now. If this assumption is wrong, please correct me, that you guys do not remember the change of variable formula with the Jacobian formulation for multivariable calculus or real analysis, or if you do remember it, you want to avoid it like the plague. If either of these assumptions is wrong, please let me know. The whole point of this is to find a way to avoid having to use that. Okay? So now, yes?
Why are they multiplied and not added?
Because we're trying to find what's the probability that both of these things happen. And so if I'm adding the variables, really what happens is the densities are a convolution. So we've seen convolutions before. And so if we then take the derivative, this becomes the density function. So we've done convolutions plenty of times. Is now just going to be the integral x1 goes from minus infinity to infinity of the density of x1 and then the density of x minus x1 dx1. And that just, we just integrate the second one and then take the derivative. All right, so now we need to put in the densities and actually do this integration. Now we have to be careful because these densities, this formula is true when x is non-negative. It's 0 if x is less than or equal to 0. So when we substitute this in, x1 can't go from negative infinity. What's the smallest x1 can be? 0. What's the largest x1 can be? It could go up to infinity, but what happens if x1 goes up to infinity? We no longer have an x2. We just have the density at x1, the density at x minus x1. So x is now fixed. We're trying to calculate what's the probability density function at x for the sum. So if x1 goes off to infinity, where am I evaluating this? Negative infinity, and that's 0. So what's the largest x1 can go? It can only go up to x. Because once it's larger than x, this is negative. And then we would just use the 0 over here. So now, yeah, thank you. It's not been a good day in terms of just where it wants to be to pivot nicely. So we'll try this. I have a feeling I'm too close. So, nope. All right, so yeah, I'm going to just move back a little bit. So if necessary, I can motion to you to just turn it. Yes. Well, hopefully, now it's turning. Okay. See, once you hire somebody, now it's fine. All right, so this is now just the integral from 0 to x. I'm going to replace x with a t just to make the integration look a little cleaner. So the first one is the density at t. So it's going to be a 1 over 2 to the new 1 over 2 gamma of new 1 over 2. Then the density is going to be t to the new 1 over 2 minus 1 e to the negative t halves. The second piece is times 1 over 2 to the new 2 over 2 gamma of new 2 over 2 x minus t to the new 2 over 2 minus 1 e to the negative x minus t over 2 dt. All right, let's pull a bunch of things out. We can pull 2 to the new 1 plus new 2 over 2, gamma to the new 1 over 2, gamma to the new 2 over 2. Now we have a e to the negative t halves. We have an e to the positive t halves. Those cancel. We have an e to the negative x halves, which we can pull out. And now we're left with an integral. T goes from 0 to x of t to the new 1 over 2 minus 1, x minus t to the new 2 over 2 minus 1 dt. And that's the integral we need to evaluate. Okay? Any thoughts on how to evaluate this integral? It's not a pleasant looking integral. Okay, now unfortunately new 1 need not be an integer. New 1 and new 2 need not be integers. So if you try to integrate by parts, you can't be promised that eventually one of the terms is going to go all the way down to 0. How well do we need to understand the value of this integral? This is going to give me a function of x, right? If I integrate this function on x from 0 to infinity, what do I get? I get 1, because this is a probability density function. So really, all I need to do is I need to just figure out what is the x dependence here. Because whatever else is left over, it's just a constant. And then if I can then integrate the x dependence, that constant has to be whatever I need to make this a probability density function. So this is the key idea. This is the idea of normalization constants. We don't have to evaluate everything perfectly. We just have to sniff out the x dependence. So over here, I have an x minus t. I'd love to pull out an x. I can't pull out an x because I have a t here. What should I scale t by? I'm sorry?
Do you mean like scale by x?
Yeah, I want to replace t with maybe x times u. You're saying multiply by x over x. I want to basically have this as x times t. I can't just put in an x. But I can let t equal x times u. and then I have an x here. I get an extra x over here, and I can pull out all those x's. So let t equal xu. dt is going to be x du. And now, what's the range for u? U is going to go from 0 to 1. OK, so what I'm going to do now is we have some constant in front. I'll call that just c of nu 1, nu 2. I have the e to the negative x halves. And now I have the integral u goes from 0 to 1. I'm going to get a xu to the nu 1 halves minus 1. Then an x minus xu to the nu 2 over 2 minus 1. And then I'll get an x du. So if I pull out all the x's, c nu 1, nu 2, e to the negative x halves, I get an x to the nu 1 over 2 minus 1 and x to the nu 2 over 2 minus 1 plus an x. So I'll get x to the nu 1 over 2. Let's do nu 1 plus nu 2 over 2 minus 1. Integral u goes from 0 to 1 of u to the nu 1 over 2 minus 1, 1 minus u to the nu 2 over 2 minus 1 du. Does this integral have any x dependence? It's just a constant. So we now get constant times constant c nu 1 nu 2, x to the nu 1 plus nu 2 over 2 minus 1, e to the negative x halves. That's exactly what we haven't erased over here. This over here is the x dependence of a density that's a chi-squared random variable with nu 1 plus nu 2 degrees of freedom. So looks like a density that is a chi-squared random variable with nu 1 plus nu 2 degrees of freedom, with parameter nu 1 plus nu 2. So that means whatever this is over here, it's exactly what I need for this to integrate to 1. So I didn't show that this integrates to 1 as an exercise. If there was homework, you would calculate that this integrates to 1. So we now know exactly what this is. This has to be equal to 1 over 2 to the nu 1 plus nu 2 over 2 gamma of nu 1 over 2 gamma of nu 1 plus nu 2 over 2. And what this tells us is, because we know that this involves a product of two gamma functions, if we can actually evaluate what this integral is, we actually have an identity now involving the gamma function. This is one of the most powerful techniques I know for integrating. It's essentially integrating without integrating. Is we pull out the dependence we care about, and we're left with something. And because we have a probability distribution, we know at the end of the day what we're left with has to integrate to 1. So because it has to integrate to 1, I'll just give it a temporary name. We'll call it C. And then at the end of the day, I have something with the x dependence. I know I can integrate that. And then this constant has to be just whatever is necessary so that at the end of the day, I have a density. So this is a truly spectacular approach. If you want to understand just how great this is, try to evaluate that integral. It can be done. I was recently in a meeting, and I was talking about one of my favorite proof techniques, the method of divine inspiration. And it turns out that a member of the committee was a religion professor, and she had never heard of proof by divine inspiration. And I found it very interesting that the math department has the method of divine inspiration, but religion does not. But we know what this constant is, right? That means you can work backwards and figure out what that integral should be. And if you know what that integral should be in terms of gamma factors, that can give you an idea of how to adjust things and how to approach things. Yes?
So how do you know that integral is constant?
Which? This integral?
Yeah.
This has no x dependence. I'm integrating u goes from 0 to 1, and everything in here depends on just u or nu 1 and nu 2. There's no x dependence. So at the end of the day, this is just a number. The integral we had over here before, thank you. The integral we had before over here, this involves x as well as t. So when we integrate out t, there's still going to be some x dependence. So this integral is a function of x. This integral is just a constant.
Isn't u equal to t over x?
U is equal to, I'm making a change of variables. So x, right now, I've fixed a value of x, and t initially ranges from 0 to x. That's the same as having u range from 0 to 1. So you're absolutely correct. U does equal t over x. But now think of it as I'm measuring my variable in units of x. And t goes from 0 to x, u goes from 0 to 1. It tells me how far have I traveled. And so when the dust settles, this integral should depend on x at the end of the day. X is a bound of integration. X is included in the integrand. And I'm only integrating with respect to t. It would be remarkable if this integral was independent of x. It's possible. Maybe everything is canceling in a miraculous way, but unlikely. This integral over here, there's no longer any x dependence. The only variable in sight is u, and at the end of the day, we've integrated out u. So because we know this is a probability density, we know that this expression here has to integrate to 1. So since I know what the integral of this is, I can then figure out what that normalization constant is. But I really don't need that value of the constant until the very end. So I can leave it as, let's just call it c. And then we'll figure out what c is later. So once we get to this point, this is an easy x integral to do. So it's a backdoor way of getting this integral. Any other questions? Yes?
Are we waiting for the snowball to
Oh, wow.
or just no?
There is a puddle, a very well-contained puddle. So yeah, I'm gonna see if this will work any better. All right. So it did not last that long. Did not have time to get a larger snowball. Okay. So the reason this is going to be useful for us is we're going to try to understand the joint distribution of the eigenvalues. And really what we care about is the spacings between the eigenvalues. What's the gap between eigenvalues? And that's going to be a very nice answer. It turns out that the answer for the 2x2 case is almost the answer for the general case. And it's almost the case for the limit. And the 2x2 case has a nice, clean, explicit formula. So frequently, when people draw plots of what the limit should be, they just lie a little bit and just draw the answer for the 2x2 case, because it's so close that this way they get to avoid something called an infinite Fredholm determinant, which sounds like something you want to avoid. And so yeah, it's within 1%. That's close enough. All right. So let's go back to what's going on. So we want to study our matrices. Okay, and so given a matrix A, I just want to do things consistently in the book. I'm doing it Q transpose lambda. Okay, Q transpose lambda Q, and so here I'm putting the minus sign down below. So it's cosine theta, sine theta, minus sine theta, cosine theta, lambda 1, lambda 2, 0, 0. Cosine theta minus sine theta, cosine theta. And just for convenience, I'll write this as x, I think y, y, z. Yep. Okay. So here's my 2x2 matrix. Here are my three free parameters, x, y, and z. Over here, my parameters are theta, lambda 1, and lambda 2. What I love about this is quite misleading as to what's going to go on in the general case. In the 2 by 2 case, we have 2 eigenvalue parameters and 1 angle parameter. In the n by n case, how many eigenvalue parameters do we have? N. But there's on the order of n squared free parameters. So as you go further and further up, more and more of your variables are the angles. These are basically coming from the eigenvectors. Cosine, sine, and minus cosine, cosine.
Sorry, could you say that again?
Sure. We have 3 parameters, theta, lambda 1, lambda 2. It looks like we have a lot more eigenvalues than angles. We have twice as many eigenvalues as angles.
But that relationship switches.
That relationship switches because if we have a real symmetric matrix, we have n plus 1 over 2 degrees of freedom. We only have n eigenvalues. We have to choose the main diagonal and then the upper part. We never do the bottom, right? We choose the main diagonal and the upper. So we have n plus 1 over 2, which is approximately n squared over 2 variables. There are only n eigenvalues. N divided by n squared over 2 goes to 0. So in the limit, almost none of the free parameters are eigenvalues. Most of the parameters are actually angles we don't care about, that we want to just integrate away. And so what I'm hoping you're beginning to see is that there's going to be a change of variable going on. We're going to want to convert from doing integration over x, y, z to integration over theta, lambda 1, lambda 2. How do we convert? I'm sorry? Well, polar coordinates is for 2-dimensional circular stuff. So we multiply everything out, and we can get x as a function of everything, y as a function of everything, z as a function of everything. This is where I am happy to refer you to this beautifully well-written textbook. And you can go through the book and just do the algebra. You just have to multiply 2 by 2 matrices. So I'll list just one of them. Well, I guess I'll list all of them. So if you do the multiplication out, you'll get cosine squared theta times lambda 1. Actually, let me just put the lambda 1 in front. Should have written it like that years ago. Lambda 1 cosine squared theta plus lambda 2 sine squared theta. The next one is minus lambda 1 minus lambda 2 cosine theta sine theta. Same thing down here. And then lambda 1 sine squared theta plus lambda 2 cosine squared theta. So there is our matrix. And so x is just lambda 1 cosine theta squared plus lambda 2 sine squared theta. So, x as a function of lambda 1, lambda 2, and theta would just be lambda 1 cosine squared theta plus lambda 2 sine squared theta. Okay? So have you done the change of variable formula in real analysis? Or was the only time you saw it in your careers in multivariable calculus? But we want to go from integrating something in XYZ space to integrating something, I guess I'm doing lambda 1, lambda 2, theta, d lambda 1, d lambda 2, d theta. And we'll have some region here v, we'll have some region here v tilde. We need to figure out how to transfer, right? Now, we know what the probability density function is in XYZ space. We're choosing the entries from independent random variables. They're Gaussian. It's a different Gaussian on the main diagonal than on the off diagonal. So we know what the f of XYZ is. we need to figure out how to transform it. Well, transforming f to f tilde, that's no problem. That's basically saying, look, wherever I have an x, replace it with this crap. Wherever I have a y, replace it with that crap. Z, same thing. But we need to figure out how the volume element transforms. So we need to figure out how do we go from dx, dy, dz to something d lambda 1, d lambda 1, d lambda 2, d theta. So how do we take the transform? So this is the change of variable formula. This is where you put in the determinant of the Jacobian. And there's two ways you can do it. Because they're just transposes of each other, and the determinant of a matrix and its transpose is the same, it doesn't matter if I flip the definition of the Jacobian. And so the Jacobian will be dx, d lambda 1, dy, d lambda 1, dz, d lambda 1. And then dx, d lambda 2, dy, d lambda 2, dz, d lambda 2. And then we'll have dx, d theta, dy, d theta, and dz, d theta. And then we'll take the determinant of that. Joy. Okay?
And what about the volume you want to, or the area you want to integrate over? Do you just calculate that explicitly?
Well, then we would figure out what the ranges would be.
From those formulas that you wrote out?
Right, so I mean, basically theta will go from 0 to 2 pi, and the lambdas will go from minus infinity to infinity. Now, sometimes what we do is we sometimes might assume lambda 1 is the largest eigenvalue. And so if we put that in, then we have the restriction that lambda 1 is greater than or equal to lambda 2. So we might do that. Maybe we'll assume lambda 1 is greater than or equal to lambda 2, just in terms of we have some freedom when we choose the matrix Q and the matrix lambda. So make lambda 1 the largest. Okay, anybody interested in calculating the determinant of the Jacobian? Okay, let's figure out how much we need to understand it. Okay, so let's look at stuff. So here's x1. When we take the derivative of it with respect to lambda 1, what do we get? Something involving just theta. When we take the derivative of y with respect to lambda 1, we get something involving theta. When we take the derivative of z with respect to lambda 1, we get something just involving theta. So the first row of this matrix no lambda 1 and lambda 2. We all agree? The second row, same argument. No lambda 1, lambda 2. Could I calculate the theta dependence if I wanted to? Yes. It's nice to be a professor. I don't want to. I don't have to. We don't have to, right? We're going to use the theory of normalization constants. This is why we started the day with that lesson on the chi-squared random variable. What about the third row? Well, the third row, now we're taking derivatives with respect to theta. Now things are more interesting. So when I take the derivative of this with respect to theta, I'm sorry?
All three still remain, right?
All three remain. So now we've got to do a little bit more work. This is the easiest one. When I take the derivative of y with respect to theta, I'm going to get something that involves lambda 1 minus lambda 2. When I take the derivative of this with respect to theta, I'll get 2 cosine theta minus sine theta. And here I'll get 2 sine theta cosine theta. Oh, I'm going to get lambda 1 minus lambda 2 times something in theta. And when I take the derivative of this with respect to theta, I'm also going to get a lambda 1 minus lambda 2 times crap in theta. So does everybody agree that when we take the derivative of each of these three pieces with respect to theta, it's always going to be lambda 1 minus lambda 2 times something involving theta? Okay. So now, over here, it's lambda 1 minus lambda 2 times a function of theta. So when we take the Jacobian and we take the determinant, if you multiply every element of a row of a determinant by 5, what does that do to the determinant? So now we have to recall linear algebra. If I multiply every row of a matrix by 5, what does that do to the determinant? By how much?
25. That's squared.
Well, let's take the identity matrix. Okay, so whenever you want to try to build intuition, start with something simpler. If we have the identity matrix and we multiply one of the rows by 5, how much has the determinant changed by? By 5. You can pull out a constant from a row. If I multiplied the entire matrix by 5, then it would be 5 squared because it's a 2 by 2 matrix. But if I multiply just one row by 5, I just changed the determinant by 5. What this means, and this is the beauty, and I can now erase all this crap, is the Jacobian is going to be lambda 1 minus lambda 2 times some horrendous function of theta. So the Jacobian is just lambda 1 minus lambda 2 times g of theta. Could I figure out g of theta if I wanted to? Yes. Could I integrate g of theta? Maybe. It's going to be a messy thing involving trig functions. And it's not clear that I would be able to evaluate in closed form. OK, now we want to just figure out what the different probabilities are. And so we need to go back and get the densities. So they were slightly different on the main diagonal than on the off diagonal. Here it is. So what I'm going to do is I'll do the case, C equals 1 from before. So we'll have the probability of x, which was our A11 from before, is going to be 1 over square root of 4 pi e to the negative x squared over 4. The probability of z, which was our A22, is also 1 over the square root of 4 pi e to the negative z squared over 4. And then the probability of y, which was our A12 piece, is going to be 1 over the square root of 2 pi, I believe, e to the negative y squared over 2. OK. So what we want to do now is we want to figure out what is the function f of x, y, z. We know that we're going to have this Jacobian coming in. And we know a lot of what that Jacobian looks like. So f of x, y, z, so we're going to have 1 over, I'll just do it as 32 pi cubed, square root. That's our constants. And then we'll have e to the negative x squared plus 2 y squared plus z squared over 4. And so we have a y squared over 2. Everything else is over 4, so I double the y. If you want to write this in terms of what we had before, x squared plus 2y squared plus z squared. This is A11 plus 2 plus A12 A21 plus A21 A22 plus A22 A22. So I'm having a little fun in terms of how I write the 2y squared in the middle. Because A12 is the same as A21. Does this look like anything? A11, A12 plus A12, A21 plus A21, A22 plus A22, A22. I'm sorry? It is quadratic, but it's a nice function of the matrix. I'm sorry? It's the trace. But the trace of what matrix? The trace not of A, given that it's quadratic, what would you guess? A squared. So if you actually just do the calculation for what's the trace of A squared, this is the trace of A squared. What do we know about the trace of A squared? We've used this result many times. It's the sum of the eigenvalues. So this would be lambda 1 squared plus lambda 2 squared. We can express this very nicely in terms of lambda 1, lambda 2, and theta. Okay? This is the amazing simplification. We start off with our function of x, y, and z, the matrix elements, but the probability density is just a function of the trace of A squared. A similar result holds in the n by n case.
So that function itself won't actually have theta in it, but when we change the d's, that's where we get the...
That's where we get the thetas. So the function itself never has any theta dependence, but the volume element transforms does. Okay. So now, I should put pieces of tape down because this seems to be working. So now we can do our integration. And now we get that the integral over v of f dx dy dz is our integral. So lambda 1 goes from minus infinity to infinity. Lambda 2 goes from minus infinity to lambda 1. And then theta goes from 0 to 2 pi. And then we'll have our constant with the square root of 1 over 32 pi cubed e to the negative lambda 1 squared plus lambda 2 squared over 4. And now we multiply by lambda 1 minus lambda 2 g of theta d theta d lambda 2 d lambda 1. Okay. So when we do the theta integration, we get just some constant. So we'll get some constant. Integral lambda 1 goes from minus infinity to infinity. Lambda 2 goes from minus infinity to lambda 1. Lambda 1 minus lambda 2 e to the negative lambda 1 squared plus lambda 2 squared over 4. And what should this integral be? So we're integrating over the entire space. So what should this integration be? It should just be 1. And now we've got d lambda 2, d lambda 1, and this should just equal 1. So we can now figure out what the value of the g theta was, what its integration was. Okay, how much time do you have left? So this gives us this gives us a way to figure out c. And now if we wanted to calculate what's the probability that lambda 1 minus lambda 2 is in a given interval, we have to evaluate this integral.
But we took all of the...
Right, because
that's in the c.
that's exactly what the c is. And so if you want as an exercise, if I'm ever mad at a class, what I would do is say, calculate the Jacobian and then do the theta integration explicitly. And that's where you say, well, let's see, how many homework problems do we have a semester? How much is this one worth? Okay, this one is probably not worth doing. And it might be the case that the 2x2 case isn't so bad. Now, before you think that the 2x2 case might not be so bad, what's the size of the Jacobian? It's 3 by 3. So you'd actually have to take the determinant of a 3 by 3 matrix where the terms could be quadratic in sines and cosines. So you could potentially have polynomials up to degree 6. Exactly. So, for those of you who are watching at home, there were several grimaces among the students. All right. It is not a calculation you want to do. All right. So now that we have this, it's not that bad to pass from this to the probability density functions and all that stuff. I don't want to do this because we've only got about 5 minutes left. Have I shown you the integral of f computation? I've done this in some of my classes. So I define the operation integral of f means integrate from 0 to x of f of t dt. Have I done this in any of my classes with you? Okay, so my freshman physics professor, who became my mentor, well, if it was in a class that you've seen, since the only class you've taken with me is operations research, right?
I may have seen this in a different
Oh,
class.
okay. I would be very curious if you've seen this in another class. So my freshman physics professor showed me this so that we would have something to think about over Thanksgiving. All right, so define this operation to mean integrate your function from 0 to x. I want to solve the integral of f equals f minus 1. All right, so just rearranging, this is the same as f minus the integral of f equals 1. All right, this is 1 minus the integral acting on f equals 1. What should I do now? Don't worry about whether or not the operation is justified. What should we do?
You could divide by it.
So you could divide by it. So we'll multiply both sides by 1 minus integral inverse. So then we get f is 1 minus integral inverse acting on 1. All right. I will put a little star as I'm a little worried about this step. Now what should we do? What does this kind of look like? Where have we seen something like this before? Would it help if I wrote it as 1 over 1 minus integral? It's a geometric series. What should you do with a geometric series? Expand it. So f is equal to 1 plus integral plus integral integral plus integral 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 acting on 1. All right, I'll put a little star over here because I'm a little worried about that step too. What should we do now? So we have this whole infinite sum acting on 1. Now what do we do? Don't worry about whether or not the step is justified. What would you like to do?
Like start applying the integrals?
So how do you apply them? We have the infinite sum applied to 1 is the sum of the applications. So this is just f equals 1 plus integral of 1 plus integral integral of 1 plus integral 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 of 1 plus dot dot dot. Well, let's see. The integral of 1 is I integrate from 0 to x of 1 dt. That's just x. So I have f of x is 1 plus x. Now, integral of 1 is just the function that's x. So I now integrate the function that's x. So that means I integrate from 0 to x of my function I write it as t dt, which is what? X squared. It is divided by 2, but I'd like to phrase it differently. Divided by 2 factorial. What's the next piece going to be? I now integrate t squared over 2 factorial. I'll get x cubed over 3 factorial. So I get f of x is e to the x. And we'll star that step because that step's also questionable. Let's check, does e to the x work? Well, if I take, f of t is e to the t, I'll get e to the t evaluated x minus e to the t evaluated 0, so I get e to the x minus 1? Yes. So the function e to the x satisfies this equation. Is this the only function that satisfies this equation? One of the big themes this semester has been we can interchange operations. We have ways to justify it. After a while, it sounds like a broken record. You know, oh, the integral is rapidly decaying, or we have enough differentiability that, you know, we can justify the following. So I thought, you know, I've been saving this, and I was hoping that it would also work out to be the Thanksgiving because that's when I learned it. You know, I've been saving this because it's about a 5-minute snippet. And this is one of the differences between my class and my wife's classes, where, you know, each day for her is a fixed unit. Whereas in math, we can just keep things in reserve, and then just when we have a break in the day, we can come and get to it. Can you justify this? For what space of functions is this valid? I don't want to define it. I'll leave that for you to ponder. Let's imagine that there's a way to define a norm on the space of operators, and that we can attach a norm, a size, to the integral operator. What would you like to know about the size of that operator? Based on what we want to do later, what would you like to know about the size of that operator on the space of functions we're studying? Because we're going from the inverse operation, 1 minus integral inverse, is this infinite sum. What do you think should be true about the size, the norm of that operator? It should be less than 1. If it's less than 1, maybe this actually makes sense in an operator setting. That we can define a space of functions where this operator has a norm of length less than 1, which allows us to have an expansion like this. Yes?
What do you mean by norm of an operator?
I am being deliberately vague. I am deliberately not giving you too much. I want you to have things to think about in case, you know, dear aunt or uncle is repeating a story you've heard far too many times, or you are stuck in a situation. Well, you can either bring it up or you can just be thinking about it and nodding your head. So just, I am deliberately not saying what I mean by norm. It's, you know what the size of a vector is. You know what the size of a number is. There are many different ways to talk about the size of a matrix. One of the ways you can define a size of a matrix is, you know, maybe the largest eigenvalue, or maybe the largest element. And different notions work better. Maybe you do the sum of the absolute values of all the entries of the matrix. Is there a good way to define the norm of an operator so that this is all justified? Okay, I will stop here.